Well, hello there. So now we're going to take our mesh current method and extend it into the realm of the supermesh. So we've reviewed these on the last couple of videos, but these are the steps for the mesh current method, and let's see how they work. So the idea of a supermesh is when we have a current source that's between two meshes. When two meshes have a current source in common, then the best approach for the analysis is to use a supermesh. The main reason is because the voltage across a current source is unknown. So when we want to do Kirchhoffs voltage law, we don't know what to put for the voltage across this current source here. So we could add another unknown and use some equations and make the system more complicated. But if we do the supermesh approach, we avoid that unknown voltage and keep our number of equations manageable. So the process is to find a loop that ignores the branch with the current source. So our supermesh is a new loop that goes around all the rest of the branches, and we'll write an auxiliary equation making sure that this current is the sum or difference of the mesh currents. So here's an example. You might notice that the layout of this circuit is a little funny. You could easily lay this out with the normal vertical and horizontal wires, but just to be different, this has a triangle shape on the top, and this current source is tied into the nodes over here. You could have tied them in up here and made new connections, but it makes it clear where the nodes are, I suppose. Anyway, we're just going to analyze it. So the first step is to identify all the meshes. So we're looking again for the open windows. So here's the I1 mesh, the I2 mesh, the I3 mesh, and the I4 mesh. But we're not quite done with step one. We also need to find super meshes. So whenever you see a current source like this, you have to say, is it all by itself? Does it only touch one mesh current? And if it does, then your life got easier. Here, this 3 amp current source is between the I4 mesh and the I3 mesh. So we need to add super mesh that avoids this. So a combination of I3 and I4 that doesn't go through their shared branch. So that's the dashed line here going clockwise. And I like to label all of the voltages across the resistors because I think it makes it easier to keep track of the signs on Ohm's law. But as you get good at this, you could probably skip this and do it in your head. Okay, so the next steps are to use Kirchhoffs voltage law on each mesh, including the super mesh. So we'll start off with the I1 mesh here, and we'll do Kirchhoffs voltage law. So -6 plus V2 minus V3 plus V1 equals 0. So a little bit of a curvy path. Then we do Ohm's law for all of the resistors. So here V2, I1 is going from plus to minus, so that's the normal sign convention. So V2 equals I1 times 10. V3 is here, and we've got I2 going from plus to minus, and I1 going from minus to plus. So V3 is 2 ohms times I2 minus I1. That's the equation over here. V1, we've got I1 going from plus to minus and I3 going from minus to plus. So 4 ohms times I1 minus I3. Combine the voltages into the Kirchhoffs voltage law, and we get this equation here. Mesh 2, it's the triangle mesh up here at the top. We're going to go clockwise, and we'll get the same process. So plus V3 plus V4 minus V5 equals 0. V3 we already had from the last time through. V4 is all by itself here, and current is going from plus to minus. So V4 is just 2I2. And V5 here, we've got I2 going from minus to plus, and I4 going from plus to minus. So V5 is 2I4 minus I2. pay attention to the Ohm's law sign convention here when you're subtracting your currents and labeling the polarities. When we combine these together, though, we get this equation here, and you can see that that pattern we've been looking for all along holds, and it really is independent of how you label the polarities here, because then you use Ohm's law and it all works out in the end. But we've got the I2 mesh, positive terms on I2 and negative terms on the other currents. So now we get to do the super mesh. So we're avoiding this branch that has the current source in it, and we're going to use all the other branches here and go around this path. So minus V1 plus V5 plus V6, and we're done. So that equals 0. V1 we got in one of the other steps. V5 we got in one of the other steps. And V6 we've got I4 going from plus to minus, so V6 equals 4 ohms times I4. Combine all of these together, and we get this equation. This is for the super mesh, so it's meshes 3 and 4, just one equation. So we also need another equation, so we have the same number of equations as unknowns. And here this is the super mesh auxiliary equation. We have to use the fact that there's 3 amps here, and we have to look at the arrow directions on I3 and I4 that are touching the 3 amp. So I4 goes up, so it's the same direction as the 3 amps. I3 comes down, so it's in the opposite direction. So the 3 amps has to be I4 minus I3. If I3 gets big, this 3 amps would have to get smaller. So I4 minus I3 equals 3. That's our auxiliary equation. So now we ended up with we have 4 meshes. We ended up with 4 equations, 2 regular mesh equations, a super mesh equation, and an auxiliary equation. One interesting thing that is a good thing to check to make sure you didn't do any really simple mistakes by confusing what kind of an element is to see what are the units of these equations. So these mesh equations here, they're based on Kirchhoffs Voltage Law. So even though we see currents, the units are volts. We have a 6-volt source here, so we know that's volts. But ohms times amps, V equals IR, so that's volts, volts, and volts. So if you're writing these equations and you add in something with amps as its units, that's going to be a mistake. So the units have to be consistent through an equation. Kirchhoffs voltage law is in volts. Kirchhoffs current law, back in node analysis, has units of amps. This is in volts because it's Kirchhoffs voltage law. This one is talking about current sources, so its units are amps. Solve the 4x4 system, and we get this set of results. All right, so now we've seen just about every aspect of the mesh analysis method with its 3 steps. Kirchhoffs voltage law and Ohm's law are the basis. Voltage sources, no problem, and current sources either make it easy by reducing one of the unknowns or a little more complicated by forcing us to use the supermesh. So now that we've seen both node and mesh analysis, you might say, which one should I use? And the answer is they both work for any circuit, so you could use either one. The reasons you might choose one or the other, some of them are listed here. In node analysis, we solve for voltages, so that might be one of the primary things. If you want to know the voltages in a circuit, node analysis gives them to you. If you need the currents, you could do node analysis and then a post-processing where you solve the currents. Mesh analysis solves for mesh currents. So if you want currents, maybe do mesh analysis because it will give you the answers. Okay. If you find the currents, you can go back and get the voltages as a post-processing step. So either way will work, but node analysis directly gives you voltages. Mesh analysis directly gives you currents. Sometimes a more important thing is how easy it is to get a system of equations. And looking at the 2 techniques, you can have a very different number of unknowns and equations. So for every node you have an equation. Every unknown node voltage, you'll have an equation, n equations for n nodes, where with meshes, you'll have m Kirchhoffs voltage law equations for m mesh loops. Sometimes if things are like all in series, you can have maybe just one mesh loop, but a whole bunch of nodes. If things are all in parallel, you can have a bunch of loops, but maybe one or two nodes, or 3 or 4 nodes, or something like that. So count the nodes and count the meshes and use whichever one makes a smaller system of equations. All right, so now you are experts at both node and mesh analysis. So we'll start looking at applications of those two techniques in the next module. See you in the next video.